Good morning friends. In this video we are going to discuss about the basic operation of bipolar junction transistor. We can shortly call it as BJT. There are two types of BJT. One is NPN, another one is PNP. The N stands for N-type semiconductor and P stands for P-type semiconductor. In NPN transistor, P is sandwiched between two N-type semiconductor, and PNP transistor, N is sandwiched between two P-type semiconductor. We know that when N-type semiconductor and P-type semiconductor come in contact with each other, this point, the contact point, we can call it as junction. So an NPN transistor has two junctions and the PNP transistor has two junctions. BJT is a three-terminal device. There are three terminals, namely emitter, base and collector. So this is emitter, this is base and this is collector. The junction formed between this emitter and base, that is this junction, is called as emitter-base junction. The junction formed between this collector and base, this junction is called collector-base junction. Now the next thing is about the bias. When P-type semiconductor is connected to the positive terminal and N-type is connected to the negative terminal, we will call it as forward bias. When P-type is connected to the negative terminal and N-type is connected to the positive terminal, we will call it as reverse bias. So, depending upon the bias, whether it is a forward bias or reverse bias, we apply to this junction. There are four modes of operation, namely saturation, forward active, inverse active and cutoff. For example, if you apply a reverse bias to the emitter-base junction, so this is emitter and this is base. If you apply a reverse bias, what does it mean? If it is connected to the N-type, so it should be connected to the positive terminal and this P-type is connected to the negative terminal. So this is a reverse bias which is applied to the emitter-base junction and a reverse bias applied to the collector-base junction. So N is connected to the positive terminal and this P is connected to the negative terminal. This is positive, negative. So we have applied a reverse bias to both these junctions. So under this condition, the transistor will be operating in the cutoff mode. So there are four different modes of operation. The next is why the name is called bipolar. The current flow is due to the flow of both electrons and holes. Hence the name is bipolar. The last point is the voltage between the two terminals controls the current through the third terminal. This is the transistor action that we will discuss in detail in the next page. Now, we have taken one of the modes called forward active mode. In forward active mode, the emitter-base junction is forward biased and the collector-base junction is reverse biased. We can see an NPN transistor here. This is emitter and this is base and this is collector. This is the emitter-base junction is forward biased and this is the collector-base junction which is reverse biased. So under here the transistor is called as an amplifying device. We will discuss in detail why it is called so. So first thing is what happens when the emitter base is forward biased. So this N-type, the majority carriers are electrons. The N-type is connected to the negative terminal, you can see, and the P-type is connected to the positive terminal. The first what happens is the electrons without the majority carriers in N-type, because of this applied forward bias, they started moving from N to P. We can see the arrow mark here, it stands for electron injection. Electron is injected from the N to P-type. That's the first thing happens. The next is coming to this collector-base junction, which is reverse bias. If you apply a forward bias, we can see the flow of current across the junction. If you apply a reverse bias, there is no, because this collector-base junction is reverse bias, we could not see any flow of current. We can see this picture over here. This is the base. The same picture is here. This is the base. So this side is emitter and this is base and this is collector. So whatever the electrons getting injected here, all this is electron injected from the emitter to the base. What happens here? The first thing to see is this base collector junction is reverse bias. What happens with a reverse bias? There is an increase in the width of the depletion region. So the depletion region is depleted of any mobile charge carriers. So it will have immobile ions like this. You can see the direction of the field, electric field from positive charge to negative charge. So now what happens here is the electrons which is injected from emitter through the base reaches whenever it reaches the collector base junction. Due to the strong electric field, these electrons will swept across this collector base junction and then the electrons will reach the collector. I will repeat it again. The electrons which are the majority carriers, because of the forward bias being applied, they get injected into the base. The base is normally kept very small so that whatever without any recombination, the electrons which are injected into the base will reach the collector base junction. Because of this strong electric field, whatever the electrons reaches towards the junction will swept across the junction to reach the collector. Now what happens inside the base? We can see two different curves. One is a linear curve, another is a straight line, another is a curved line. Here this is a base which is of p type. The holes are the majority carriers. Holes are the majority carriers. Whatever the electrons injected into the base will get, few of the electrons will get recombined with the holes. The first approximation we are making here is, we are assuming that there is no recombination in the base. Under such approximation, whatever the electrons get injected into the base without any recombination, they will reach as the collector. So if that under that condition, we can see the electron concentration as a red curve with respect to distance without any recombination. This is the ideal case. The practical case is there is some recombination takes place. So you can see the curve slightly deviates from the linearity. Now we will see the equations for emitter, collector and base current. First is emitter current. Here we can see that NPN transistor with emitter base forward biased and collector base reverse biased. The first thing is, this is the function of is same as that of normal PN diode. Consider normal PN diode. What is the diode equation? Diode equation is I naught exponential of V by Vt minus 1. So I naught is the reverse saturation current and V is the applied voltage and Vt is the thermal voltage. The same way here also we can write emitter current as IE naught exponential of VBE by Vt minus 1. So VBE is the voltage applied across base and the emitter. Now when this VBE is much larger than Vt, we can neglect this minus 1. So emitter current is approximately equal to IE naught exponential of VBE by Vt. The main point here is IE emitter current is proportional to exponential of VBE by Vt. The next is collector current. The amount of collector current depends upon the number of electrons reaches the collector. So number of electrons reaches the collector depends upon the number of electrons injected into the base. And second, the number of electrons injected depends upon again on this applied voltage. So what we can say is the collector current IC is also proportional to exponential of VBE by Vt. The one important point to note here is this base junction is reverse bias. This base junction is reverse bias. So what happens here? Even though this reverse bias, you can see the flow of current because of this forward bias junction. So this collector current, the current through the collector is controlled by the voltage applied between the base and the emitter. So the current through the third terminal, that is the collector terminal, is controlled by the voltage applied between the base and the emitter. This is called transistor action. Okay, so another thing is the collector current, we can say to first approximation, is independent of reverse bias DC voltage. Now We have seen emitter current and collector current, and the last is base current. We know that this p-type semiconductor where holes are the majority carriers. In last slide we saw that electrons are injected from the emitter to the base. Similarly, holes are injected from this base to the emitter. Okay, so there is some current due to this flow of holes. That is one of the component of the base current. This current also depends upon this applied bias VBE. So the base current has two components. The first component is due to the flow of holes from the p-type to the n-type, that is from the base to the emitter. So this is the first component. Then what about the second component? We have approximated that there is no recombination in the base, but that is the ideal case. But practically there will be few recombination will takes place in the base region. So what is recombination? This p-type semiconductor has many holes here. The electrons which is entering will recombine with these holes and get disappear. The holes get disappear. Okay, so to compensate for these holes, the base terminal will supply holes. Okay, to compensate for this loss of holes, the base term this replaced by the holes from the base terminal. So this flow of holes will contribute the second component of the base current. Again, this is also proportional to exponential of VBE by VT. So the base current has two components. Both the components are proportional to exponential of VBE by VT. So in this video, we have seen what is the basic operation of bipolar junction transistor and the current equation for emitter, base and collector. In the next video, we will see the NPN transistor in CE configuration. Thank you.